Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into something mysterious, something that flickers between science and fiction, between geometry and longing, the strange, theoretical, and endlessly fascinating idea of wormholes, gateways between stars, tunnels through space-time, and maybe, just maybe, bridges through time itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the mystery of wormholes. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So let's begin not with success, but with failure. Not with a bright flash of possibility, but with something that was meant to work, and didn't. Somewhere between the moon and Neptune in the gentle, vast quiet of deep space, there was a mission. It wasn't real, not in your world or mine, but it could have been. That's what makes it a good story. Imagine this: a spacecraft, small by the standards of interplanetary ambition, but filled with curiosity, is launched not toward a planet or a moon, but toward a wormhole, a controlled, stabilized wormhole, a test passage, a shortcut. The idea had passed every simulation, every stress test, every skeptical eye on the committee. Its entrance floated just beyond lunar orbit, invisible except to instruments and belief. Its other end opened in the cold orbit of Neptune, 9 billion miles away. What could take months by traditional propulsion, or even years, would take minutes, perhaps seconds if the theory held. And so, after a slow glide away from Earth, the probe aligned its course. It fired its manoeuvring thrusters. It entered the hole. And then, nothing. No telemetry, no ping, just silence. For a while, no one panicked. Wormhole dynamics weren't instantaneous, and data could lag. But as hours passed, and then days, the reality set in. The craft hadn't made it to the other side, nor had it returned. It had vanished, until it didn't. 500 years later, at least from the perspective of Earth, a telescope orbiting Neptune picked up an anomaly, a shape, faint, scarred, moving strangely, as if space itself resisted its motion. It was the probe, or what remained of it. It had emerged. Inside, the automated systems were long dead. No voices, no logs. The interior was twisted, subtly, unnervingly, by forces no diagnostic could explain. Time inside the craft had passed differently. Perhaps not all, perhaps too much. No crew had ever boarded it, just instruments. But the probe seemed older than it should have been, as though the wormhole had held it in a place where time forgot how to count. This wasn't a tale told to discredit wormholes or mock ambition. It was a whisper in the ear of physicists, a reminder. General relativity might describe wormholes in the language of space-time, in equations and curvatures and tensors, but it doesn't promise they'll stay open, or safe, or even real. And so, tonight, we begin our journey not by asking what wormholes are, or whether they can take us to distant galaxies, or to the past, or to the far ends of the multiverse. Instead, we begin by admitting something more profound. We do not know. We have shapes in math. We have whispers in theory. We have hopes dressed as equations. But between the moon and Neptune, something didn't work. This failure isn't meant to discourage you. Quite the opposite. It's the perfect place to begin, because science isn't made of answers, it's made of questions, and wormholes, perhaps more than anything else in theoretical physics, invite questions that go beyond what can be measured. They ask, what is distance really? What is time? What if far away wasn't so far? You've probably seen the image before. A sheet of paper, a pencil. A teacher folds the paper so two dots, once far apart, now touch. The pencil punches through. That's the wormhole, a shortcut, a tunnel through space-time. But here's the thing. That metaphor, gentle as it is, hides a storm of difficulty. Folding space isn't like folding cloth. Poking holes in reality isn't like piercing cardboard. The geometry of space-time is more like the structure of a dream than the surface of a table. It's real, but only in a way that bends your sense of what real means. And still, we wonder. Not because we expect an answer tonight, or even in 1,000 nights, but because sometimes the act of wondering is its own form of travel. Wormholes might not work, not yet. They might not exist, not in the way we imagine. But they open something in us just by being possible on paper, just by showing up in the math. So tonight, let's walk toward them, slowly, softly, one question at a time. We'll explore their geometry, we'll follow the lines of time, we'll dive into paradoxes, detour through quantum ideas, and surface again in a place that feels familiar, but different. Not because we move through space, but because space, in its own way, might have moved through us. Imagine sitting at a small cafe table late at night. The street outside is quiet, lamps casting warm pools of light across the sidewalk. You're alone with a cup of tea and a paper napkin, which you've been folding and unfolding almost absent-mindedly. And on that napkin, with a borrowed pen, you draw two dots. One near the top edge, one near the bottom. They represent two galaxies, unimaginably far apart. And then, with a small smile, you fold the napkin so those two dots kiss. Suddenly the distance is gone. This is the classic wormhole metaphor. You may have seen it in a textbook, a YouTube video, or a movie like Interstellar. It's comforting in its simplicity. The vast, cold stretches of space reduced to something you can bend in your hands. The pencil punching through the napkin becomes a spaceship darting between stars, and the napkin, it becomes space-time itself, foldable, touchable, malleable. But here's what makes the metaphor beautiful. It isn't just about physics, it's about longing. It's about every moment when there felt too far from here, every person we missed, every place we couldn't reach. The idea of wormholes isn't only a scientific curiosity, it's an emotional one. We imagine shortcuts through the cosmos not just because we want to travel quickly, but because somewhere deep down we wish that distance didn't have to mean separation. That time didn't have to mean waiting. That far away didn't have to mean never again. And perhaps that's why the idea of wormholes has stayed with us for so long. Because behind all the math and the jargon, there's a very human story being whispered. A story of connection, of reunion, of hope stitched into the very fabric of reality. Now, let's unfold the napkin just a little. Back in 1935, Albert Einstein and his colleague Einstein-Rosen published a curious paper. They were studying the mathematics of general relativity, the same theory that showed how gravity emerges from the curvature of space-time. But as they dug into the equations that describe black holes, they found something strange. A solution that didn't describe one region of space, but two. Linked, mirrored, connected through what looked, mathematically at least, like a bridge. This became known as the Einstein-Rosen bridge, the first wormhole written in the language of physics. But there was a catch. These bridges, while mathematically valid, were not stable. They pinched shut too quickly, collapsing before anything, light, matter, or even a whisper could travel through. It was like trying to crawl through a tunnel made of sand, only to find it fills itself in before you've even taken the first step. Still, the door had opened. The bridge, even if only a ghost in the math, had been seen, and that changed everything. In the decades that followed, physicists began asking, what if? What if there were ways to stabilize these bridges? Could they be made traversable? Could one, in theory, enter one end and emerge from the other, not just across the universe, but across time itself? To answer those questions, we first have to understand what space-time really is. You may be used to thinking of space and time as separate things. We move through space, we walk down a street, we fly to another country, and time, it moves through us. We grow older, clocks tick, days pass. But according to Einstein, space and time are not two separate realities. They are one thing, a single fabric called space-time, woven together so tightly that the warp and weft of one cannot exist without the other. And this fabric is not flat. It bends, it warps, it twists and curves in response to mass and energy. A star, a planet, even you sitting there quietly, cause the space-time around you to deform ever so slightly. That's what gravity really is. A curvature. Things fall toward the Earth not because they are pulled by some invisible hand, but because Earth curves the space-time beneath them, like a bowling ball resting on a trampoline. And smaller objects, like marbles, roll toward it, not because they're called, but because they follow the path laid down by the curve. A wormhole, then, is a kind of extreme curvature, not just a dip in the fabric, but a tunnel through it. A passage that connects two distant points in space, or time, by folding the geometry of reality itself. The equations allow it. General relativity doesn't forbid wormholes. In fact, it seems to permit them, at least in theory. But permitting and enabling are two very different things, because to keep a wormhole open long enough for something to pass through, something strange is needed. Something that pushes back against the natural tendency of space to collapse the tunnel. Something exotic. And this is where things begin to drift from the poetic into the peculiar. To stabilize a wormhole, you need what's known as negative energy. Not just an absence of energy, but energy that's less than nothing. Something that curves space in the opposite direction of mass. Something that repels rather than attracts. This idea may sound fictional, but quantum physics offers a glimmer of hope. In the next part of our journey, we'll explore how vacuum fluctuations and the Casimir effect might hint at how negative energy, real, measurable, albeit tiny, can exist in nature. We'll meet physicists like John Wheeler and Kip Thorne, who gave wormholes their name and tried, at least on paper, to make them real. But for now, let's return to that folded napkin on your cafe table. Maybe it's still there. Maybe your tea has gone cold. Maybe you've drawn a little rocket between the dots, just for fun. It doesn't matter. What matters is the longing behind the sketch, the quiet wish that there could be a way, not just to go farther, but to come closer, to bridge the impossible. That's the true heart of a wormhole. Not the tunnel itself, but the idea that even the vastness of the universe might be something we can gently fold. Somewhere in the folds of history, not in the farthest reaches of space, but in the quiet corridors of thought, a physicist met a mathematician. Their meeting didn't happen over coffee or under starlight, but in the quiet echo of equations. Albert Einstein, known even then for his deep and sometimes unsettling insights into the nature of reality, had reshaped our understanding of how time and space might behave when observed through the lens of motion. But something was still missing. His theory of special relativity explained much, but it had not yet found the language to describe itself fully. And then came Hermann Minkowski. Minkowski was not known for poetry, but what he proposed had the rhythm of something eternal. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." With that, the curtain lifted on a new stage. Space-time. Let's slow that down for a moment. Until that point, space and time had been thought of as separate things. Space was the stage where objects existed, moved, collided. Time was the invisible river they floated along, always forward, always away from the past. But Minkowski suggested that this separation was an illusion. The two were not distinct threads, but part of a single fabric, woven together, inseparable. He called this fabric space-time. It wasn't just a convenient metaphor, it was a literal truth, grounded in the mathematics of relativity. Imagine, if you will, a loaf of bread. Each slice represents a moment in time. Stack enough slices together and you have a volume, a life. You, as you sit or lie there, are not just a point in space. You're a stretched out ribbon in space-time. You have a length, not just in inches, but in moments. You occupy a now, but also a then, and a someday. This may feel abstract, but it's no more abstract than memory, or hope. They too are slices of time we hold on to, just like the loaf. Minkowski's space-time was more than philosophical elegance. It was the necessary foundation for general relativity. Because once you see that time and space are aspects of the same thing, you begin to understand how they can bend together. If space can curve, so can time. If motion through space slows your clock, then standing still in the right curvature can do the same. The stage is no longer flat. It can dip, rise, twist, and loop. You might picture this curvature as a kind of map distortion. Think of the Earth. On a globe, Greenland and Africa are very different in size, but stretch the globe into a flat map, and the sizes warp. Shapes grow where the fabric is stretched and shrink where it compresses. Space-time behaves in much the same way, except the map isn't of land, but of existence itself. Now, this geometry has strange consequences. For instance, what you experience, as gravity isn't a force pulling you down, it's your path bending along the curves of space-time. You're not being pulled. You're falling along the straightest possible path in a curved world. The same applies to light. A beam of light from a distant star doesn't always travel in a straight line, at least not in the traditional sense. When it passes near a massive object like a galaxy or a black hole, its path curves. And yet, from the light's perspective, it's still moving straight ahead. The space around it is what's distorted. This brings us to the deeper idea. If space-time can bend, stretch, and warp, might it also fold? If a beam of light can curve, might two far apart points come closer, not by travelling through space, but by reshaping the space itself? That is the seed of the wormhole idea. And the reason we need Minkowski's insight is that you cannot have a wormhole, a true one, unless you believe that space and time are not fixed, separate entities. You must believe that the cosmos can flex, that its geometry is soft, dynamic, and responsive to the presence of mass and energy. You must believe that the universe has, in its deepest logic, room for tunnels. But before we can dig those tunnels, we have to understand the terrain. Minkowski's space-time is four-dimensional. That means it has three familiar spatial directions: length, width, and height. And a fourth that behaves differently: time. Time flows. Or at least that's how we perceive it. But in the block universe view, the one suggested by this four-dimensional model, past, present, and future all exist together. The flow of time may be more of a perception than a fundamental motion. Like flipping through the pages of a book, one by one, we feel motion where there is only sequence. This model is not universally accepted. Some physicists favour interpretations where time is still dynamic, not frozen. But for many formulations in relativity, especially those involving wormholes and black holes, the block model works remarkably well. You might imagine space-time as a kind of cosmic stage play. Every movement, every character, every scene is already written. You're both the actor and the observer, playing your role and watching yourself play it. The drama unfolds across this four-dimensional landscape, even as you feel it moment by moment. Now let's return to that napkin from earlier. If you tried to draw a wormhole, just a sketch, you'd find yourself working in at least 4 dimensions. A tunnel that connects 2 distant places must not just exist in 3-dimensional space, it must also navigate time. A wormhole is not a tube through air, it's a shortcut through history. And if time is part of space, then it too can be folded. Einstein would go on to use Minkowski's ideas as the groundwork for his general theory of relativity. Without this union of time and space, the theory wouldn't hold, the equations wouldn't work. The idea of curved, space-time would collapse into confusion. But with it, something elegant emerges. A universe where motion is geometry, where gravity is softness, and where possibility lives not at the edge of imagination, but in the curve of reality. In the next session, we'll take that geometry further. We'll explore what happens when the curvature becomes extreme, when the stage caves in on itself, creating a black hole. And we'll look at how that collapse leads, quite unexpectedly, to the first whispers of a bridge made not of stone or steel, but of equations, a mathematical thread, fragile and fleeting, connecting 2 regions of space, the first theoretical wormhole. But for now, let this idea settle. You're not moving through time, you're unfolding in it. If space-time is a stage, as Minkowski so gently proposed, then Einstein was the one who showed us how that stage can bend. Not with the slapstick abruptness of a trapdoor, or the violence of a collapsing roof, but with grace, curving softly around stars, bowing beneath planets, rippling like a silk sheet caught in motion. General relativity is many things: a theory of gravity, a set of equations, a towering pillar of modern physics. But it is also, in its essence, a story about how matter shapes the world around it, not through pulling or pushing, but by warping the very fabric of where and when. To understand this, let's start not with distant galaxies or hypothetical black holes, but with something simpler. An apple. We all know the story. Newton watches an apple fall and wonders why. His answer, elegant and bold, was gravity, a universal force pulling objects toward one another. Mass attracts mass. The apple falls to the ground because Earth exerts a force upon it. It's a model that worked beautifully for centuries, and it still works well enough to put satellites into orbit and spacecraft on Mars. But Einstein saw a different story hidden beneath the same event. He imagined the apple not as being pulled, but as following its natural path through a landscape that's been subtly bent by Earth's presence. It's not falling, it's rolling along the curve of space-time, and Earth isn't reaching up to grab it. Earth is simply sitting there, heavy and unmoving, and space-time curves around it like a blanket drawn in. In this new view, gravity is not a force at all, it's geometry. Let's turn, briefly, to a helpful metaphor. Picture a large trampoline stretched tight and smooth. Place a heavy bowling ball in the centre, and the surface dips. Now roll a marble along the edge. It curves inward, not because the ball is pulling it, but because the surface it travels on is no longer flat. The marble is doing its best to move in a straight line, but straight lines aren't what they used to be. They've been bent. This is how light behaves near massive objects. It bends not because it has mass, but because the space through which it moves is curved. When you see the light from a distant star being distorted or magnified by the presence of a galaxy in between, what astronomers call gravitational lensing, you're not seeing an illusion. You're seeing geometry made visible, and just as light curves, so does time. In general relativity, time slows down near massive bodies. Clocks tick more slowly on the surface of Earth than they do in orbit. This isn't science fiction. It's science fact. It's something we must account for every day in GPS satellites. Without correcting for gravitational time dilation, your phone would get your location wildly wrong. Einstein's field equations describe all of this with astonishing precision. They are elegant and terrifying, compact and vast. They tell us that mass and energy tell spacetime how to curve, and spacetime tells mass and energy how to move. It's a kind of cosmic dialogue, matter speaking, geometry responding. But sometimes when mass becomes extreme, the dialogue turns strange. Imagine a star many times more massive than our Sun. It burns brightly for millions of years, fusing hydrogen into helium and then heavier elements, until at last it exhausts its fuel. The outward pressure from fusion fades, and gravity, no longer balanced, takes over. The star collapses inward, pulling tighter and tighter, until even the atoms themselves are crushed. And if no force is strong enough to halt the collapse, the result is a black hole. Black holes are not holes in the traditional sense. They are regions of space-time where the curvature becomes so intense, so steep, that nothing, not even light, can escape. At their centre lies what we call a singularity, a point of infinite density where our equations break down. It's not that the physics becomes mysterious, it's that the physics, as we know it, ceases to apply. These aren't just mathematical oddities. We've observed black holes through their effects, stars orbiting invisible companions, light from background galaxies being stretched and smeared into arcs, and now, through the direct imaging of their event horizons, the borders beyond which return is impossible. And yet, even as we observe their shadows, black holes remain among the most mysterious structures in the universe. Because somewhere, buried in the equations that describe them, is the seed of something else. When Einstein and Rosen examined these same equations, they found that certain solutions allowed not just for singularities and black holes, but for bridges, connections between distant points in space-time. These bridges would later be called wormholes, though at the time they were simply a mathematical curiosity. Not practical, not stable, but tantalizing. If space-time can be curved so extremely that it collapses into a black hole, might it also be shaped to open a path instead? Could there be a region where the geometry forms not a prison, but a tunnel? This is the heart of the wormhole idea. That curvature, extreme though it, maybe need not always lead inward. That there might exist conditions under which space-time folds back on itself, not to trap, but to connect. A bridge, not a wall. But we must be cautious. The equations may allow such things, but allowance is not guarantee. Just because a road appears on a map doesn't mean it's been paved, or even that it exists at all. Still, in the quiet of our wandering, the possibility remains. And perhaps that is enough. In the next session, we'll return to Einstein and Rosen and examine their 1935 attempt to avoid the horrors of singularities by proposing a mathematical structure that connects two regions of space. It would be elegant, symmetrical, and ultimately unstable. But for a moment, for the duration of a single page in a physics journal, it would hint at a universe that might be more connected than we ever dared to hope. By 1935, Einstein was growing increasingly uncomfortable with the singularities that haunted his own equations. These were places like the centre of a black hole, where density became infinite, where curvature of space-time broke down completely, and where the laws of physics, so carefully written, seemed to lose their meaning. To Einstein, this was not just a technical problem, it was an aesthetic and philosophical affront. The universe, he believed, should not be so inelegantly torn at its edges, and so in that year, together with mathematician Nathan Rosen, he proposed something different, something that might remove the singularities from general relativity entirely. What they discovered, or rather constructed from the fabric of their field equations, was a kind of mathematical passage, a solution that linked two distinct regions of space-time together. Not by extension, as in travelling from point A to point B across the intervening space, but by connection, a joining, like stitching together two pages with a single thread through a puncture in the margin. This was the birth of what would later be known as the Einstein-Rosen bridge, the first theoretical formulation of a wormhole. To be clear, Einstein and Rosen were not trying to create a portal through space. They weren't imagining faster-than-light ships or shortcuts between galaxies. They were attempting to solve a mathematical problem, to find a version of general relativity that didn't collapse into a singularity when describing particles like electrons. In their formulation, the bridge wasn't meant to be crossed. It wasn't even stable. It was a static solution, elegant but ephemeral. Still, the idea lingered. Imagine two black holes facing one another, not side by side in the sky, but connected through their very centres, like the tips of two funnels pressed together at the narrowest point. The Einstein-Rosen bridge envisioned such a geometry. At each end an opening, a mouth into curved space-time. In the middle, a throat linking them. For an instant, the two regions are connected, as if the universe had reached across itself. But the connection doesn't last. Not in this model. According to the math, the bridge collapses too quickly for anything, even light, to pass through. It pinches shut the moment it forms. No message can be sent. No object can traverse it. It is in that sense a mirage, visible on paper but unreachable in practice. And yet, the fact that such a structure emerged naturally from Einstein's own theory was remarkable. It meant that wormholes weren't pure fantasy. They weren't alien technology or magical loopholes invented by science fiction. They were mathematical consequences of general relativity. The universe, in its equations at least, allowed for them. Let's pause here and consider what that means. Mathematics, in physics, is more than a tool. It's a mirror. The equations we write don't just describe what we see. They hint at what might be seen if we had better eyes or more sensitive instruments or simply more time. And sometimes those equations reveal possibilities that are almost mythic, hidden dimensions, quantum entanglements, and in this case, bridges between worlds. Even though Einstein and Rosen weren't focused on interstellar travel, their work planted a seed. Others began to wonder, could a bridge like this be stabilized? Could the collapse be slowed or prevented? And if so, could someone cross to the other side? That's a question we'll explore further in later sessions, but before we move on, it's worth lingering just a little longer with the original bridge, because in its brief life, it captures something deeply human. You see, the Einstein-Rosen bridge isn't just a structure in space-time, it's a symbol, a gesture of resistance against the collapse of meaning, a refusal to accept that reality must end in singularity, in a place where nothing makes sense. It's the idea that even at the edge of understanding we might still find a way through, that even in the deepest gravity wells of our knowledge there may be light, or at least connection. And it's this emotional undercurrent, this barely whispered hope, that gives the bridge its enduring power. Even if it can't be crossed, even if it fails as a solution to the problem it was meant to solve, it remains a profound conceptual object. A place in the math where two wares become one, a point of possibility. Now, if you were to try to draw this bridge, you'd find it's difficult. Not because it's complex, though it is, but because our brains aren't built to visualize four-dimensional geometry. We can sketch the mouths, the tunnel, the idea of connection. But the true shape, the way space-time folds and curves to allow such a link, is beyond ordinary perception. Still, artists and physicists have tried. They've drawn funnels and tubes, mirrored wells and twisting corridors. They've animated simulations of matter flowing through the throat of a wormhole, disappearing in one region of space and appearing in another. These visualizations are not literal, they're metaphors, but they help. They let us feel the shape of the math, even if we can't fully see it. And that's the gift of theoretical physics. Not that it always gives us real, usable technology, but that it gives us images, ideas, possibilities that stretch our thinking. It reminds us that space is not empty, that time is not linear, and that connection may not always require movement. In the next session, we'll explore another mathematical structure that emerges from general relativity: the white hole. A theoretical twin to the black hole, it does the opposite. It expels rather than swallows. And while it too may be impossible in our universe, it offers another way of thinking about time, direction, and what it means to leave rather than to fall. But for now, rest with the image of that bridge, curved, silent and fleeting. A shimmer in the geometry, a line between 2 points that were never meant to touch, a reminder that sometimes even a path that collapses is still worth finding. Let's step for a moment into a mirror, not the kind that shows your face in reverse, but a deeper kind of reflection, a mathematical inversion. If a black hole is the great devourer, then what would its opposite be? A thing that does not consume, but only gives. A region of space from which nothing, not even light, could enter, because everything is being constantly thrown out. This is the white hole, a theoretical twin to the black hole, and just as mysterious, perhaps even more so. The idea is straightforward in its symmetry. If the equations of general relativity allow for a solution where matter and energy fall inward, forming an event horizon beyond which escape becomes impossible, then surely by reversing time in those same equations, we should be able to describe a process where matter and energy forever rush outward, forming a horizon that can never be crossed inward. And the math agrees. Flip time's arrow and a white hole emerges, every bit as valid in the equations as a black hole. But while black holes appear in nature, we've seen their fingerprints, their shadows, even images of their event horizons. White holes remain ghosts in the machinery. We've never observed one. There is so far no evidence that they exist. Why? The answer lies not just in the elegance of equations, but in something more grounded, more stubborn. The second law of thermodynamics. This law, simply put, tells us that disorder, entropy, tends to increase, that systems evolve from order to chaos, not the other way around. A cup of hot tea left on a table cools to room temperature. It never spontaneously reheats. A broken glass may scatter across the floor, but it will not leap up and reassemble itself. And here's where white holes begin to crumble, not mathematically, but physically. Because to form a white hole, you would need a situation where an enormous amount of energy and matter suddenly erupts from a single point, all perfectly coordinated, all flowing outward with the precision of reverse collapse. It would be the equivalent of watching debris on the ground leap back together into a valse, not just unlikely, but forbidden by the laws that govern entropy. Black holes form naturally through collapse, stars reaching the end of their fusion cycles, gravity taking over, the fabric of space-time yielding. But white holes would have to unform, reverse collapse spontaneously. They are, in a sense, time's backward fantasy, incompatible with the thermodynamic flow we observe in every corner of our universe. Still, the idea is captivating. Some speculative theories have proposed that white holes might exist at the other end of a wormhole, that a black hole could connect to a white hole elsewhere in the universe, or even in another universe entirely, creating a kind of cosmic flow, matter in, matter out. These models, often called maximally extended solutions, trace out the full mathematical possibilities of space-time geometry, including regions we can't access or observe. They're not practical maps, but they're beautiful ones. And then there are those who wonder whether the Big Bang itself was, in some abstract sense, a kind of white hole, a sudden, intense release of matter and energy from a single point, expanding outward into space and time. It's a provocative idea, not widely accepted in mainstream cosmology, but intriguing enough to stir the imagination. After all, we don't know what preceded the Big Bang. We may never know, but it remains one of the few observed phenomena that shares the white hole's signature. A sudden, one-way expansion from a hot, dense origin. Even if white holes don't exist in a literal observable sense, they serve an important role in the thought space of physics. They remind us that equations, while symmetric and impartial, are not always constrained by what the universe chooses to build. Just because something is allowed in the math doesn't mean it survives contact with reality. And yet, those same mathematical ghosts sometimes return, later, stranger, and more real than we ever imagined. There's also something quietly poetic about the white hole's behaviour. A black hole hides information. It swallows signals, veils its contents behind an event horizon. What falls in doesn't come out, not because it's destroyed necessarily, but because the path back is cut off by the very structure of space-time. A white hole, by contrast, is pure exposure. It cannot hide anything. Everything must leave. Nothing can enter. It's a kind of cosmic vulnerability. But again, we return to thermodynamics. The white hole's behaviour contradicts the arrow of time as we know it. To exist, it would have to begin in a state of maximum disorder and evolve into order. It would have to get younger, not older. It would have to unmix the milk from the coffee. In a universe that always moves forward in time, statistically thermodynamically, a white hole feels like a story being told in reverse. Still, if we allow ourselves to dream gently for a moment, there's a comfort in imagining that perhaps, somewhere beyond the reach of entropy, there exists a region of space-time that is nothing but light flowing out. A place that never collapses, never traps, never forgets. A fountain instead of a drain. Such thoughts, while unprovable, can be restful. They give us strange geometries to wander in, even if only in imagination. And often, that is enough. In the next session, we'll meet the man who gave these strange ideas a name. John Wheeler, physicist, poet of the void, and the one who coined the term wormhole. It was he who turned bridges into something more than math, into something we could picture, something we could wonder about. But for now, let the image of the white hole linger, a mouth that only exhales, a tunnel that never receives, a mirror held up to time, showing not what is, but what might have been, had the universe chosen to move the other way. There's something quietly powerful about giving a name to the unknown. Until it's named, an idea remains a kind of ghost, an unshaped thought, difficult to share, harder still to hold. But once a word is spoken, even if the thing it names lies beyond reach or comprehension, it gains a presence in the world. And that's what physicist John Wheeler did for wormholes. He gave them a name. And with that simple act, the bridge became something more than a mathematical oddity. It became a place in the imagination. Wheeler was not a man easily summarised. He worked closely with giants, Einstein among them, and mentored others who would one day become giants themselves, like Richard Feynman and Kip Thorne. His contributions to physics were numerous and foundational, but what set him apart was his ability to think not only with equations, but with metaphor. He had a poet's instinct for naming things just right. It was in the 1950s that Wheeler first used the word wormhole to describe the hypothetical tunnels through space-time that had emerged from general relativity. He wasn't proposing a way to travel faster than light, or to leap from one star system to another in an instant. At that time, wormholes were still deeply theoretical, fragile creatures of math. But Wheeler saw the need to call them something tangible, something that people could see in their minds, even if they couldn't yet build or observe them. And so he borrowed the idea from nature. Imagine, he said, an apple. A worm, rather than crawling around the outside, might instead burrow a tunnel straight through. From skin to skin through the fruit's centre, a shortcut. Not a path you can see, but one that exists nonetheless. This, he suggested, is what space-time might allow. A tunnel, invisible from the outside, but real enough to traverse. If only you could survive the journey. The image caught on. Scientists, writers, filmmakers, they all embraced it. Because the name didn't just describe a theoretical structure. It conjured one. Suddenly, what had been a line in an equation was now something you could imagine crawling through. The mouth of a tunnel. a soft curve in space, a secret corridor behind the stars. Of course, giving something a name doesn't make it real. And the wormholes Wheeler described were no more stable than Einstein and Rosen's original bridges. They still collapsed too quickly, still required conditions the universe didn't seem eager to provide. But the difference was this: people now cared about them. The idea had a foothold. It had weight, not in mass but in meaning, and meaning has a strange kind of gravity. From this point onward, wormholes became part of the serious conversation in physics. They were still hypothetical, still buried deep in the thickets of theory, but no longer ignored. Wheeler's vision, along with his talent for mentorship, helped plant the seed in younger physicists who would carry the idea further, exploring whether such structures could exist, whether they could be stabilized, and what strange consequences might follow. But Wheeler wasn't content to merely name things. He also posed riddles. "Space-time tells matter how to move," he said, echoing Einstein, "and matter tells space-time how to curve." But then he went further, asking whether all the physics might emerge from information itself, whether, at the deepest level, the universe is not made of particles or waves, but of bits, not of things, but of yeses and nos. This idea, sometimes paraphrased as it from bit, suggested that the structure of reality might be encoded in logic and choice, that wormholes, black holes, even time itself might be emergent from more fundamental patterns of information. It was a bold idea, speculative, yes, but quietly revolutionary. And like so many things Wheeler said, it planted a seed that would take decades to bloom. Today, as physicists explore the connections between entanglement and geometry, as they ask whether space-time itself might be woven from quantum information, Wheeler's whispers echo more loudly than ever. He didn't live to see all of these ideas mature, but his fingerprints are everywhere, especially on wormholes. Because it's one thing to write down a structure in the abstract language of general relativity. It's another to give it a name that invites wonder. That's what wormholes became, thanks in large part to Wheeler. Not just geometric artifacts, but invitations to imagine. The idea that somewhere, in the quiet curves of space-time, two distant places might reach across the void and touch. That a traveller might one day step into a darkness not to fall, but to pass through. That the universe, so vast, might also be secretly folded. Of course, Wheeler also knew the limits. He understood that wormholes were, as far as anyone could tell, unstable, that they collapsed before anything could pass through, that to hold one open might require something exotic, something not yet discovered. He didn't promise a future of interstellar highways. He only offered the possibility of a door, and that was enough. In the next part of our journey, we'll follow that possibility further, because just as Wheeler was naming these strange tunnels, another generation of physicists led by people like Kip Thorne were beginning to ask a deeper question. Not just, do wormholes exist, but could they be made traversable? Could a clever manipulation of the laws of physics allow us to actually use these bridges, to step through them rather than just imagine their shape? To answer that, we'll need to leave behind geometry for a moment and dip into the weirder waters of energy, particularly negative energy, and the strange behaviour of quantum fields in empty space. But for now, let's linger with the name itself. Wormhole. Simple, organic, quietly strange. A word for something that may not exist, and yet somehow feels real enough to matter. Let's imagine a conversation, not between physicists in a lab, but between two minds stretched across fiction and science. One writes stories, the other writes equations. Both are in love with the universe, and both are wondering the same thing. Could a person step through space and find themselves somewhere or somewhen else? It began with Carl Sagan. In the early 1980s, he was drafting what would become his only novel, Contact, a story not just of aliens, but of interstellar conversation, a quiet bridge between intelligent minds. The plot required a plausible method of long-distance travel, not for a spaceship that took centuries to arrive, but for something almost immediate, something strange but not entirely impossible. And so, Sagan did what many storytellers dream of doing. He called a friend who happened to be one of the most brilliant physicists alive. That friend was Kip Thorne. Thorne, already known for his deep work in general relativity, took the question seriously. Not because he believed wormhole travel was within reach, but because it was a beautiful problem. A scientific challenge wrapped in fiction, but guided by the laws of physics. Until that point, wormholes were mostly mathematical curiosities, allowed in Einstein's equations but known to be unstable, ephemeral, useless for travel. But Thorne asked, what would it take to make one traversable? What ingredients, however strange, might prevent it from collapsing the moment it formed? The answer, he discovered, was something radical. In a 1988 paper written with Michael Morris and Ulva Yurtseva, Thorne introduced the idea of a traversable wormhole, a tunnel through space-time that a person could actually walk or fly through. But there was a catch. To keep the wormhole open, to counteract the crushing gravitational collapse that would otherwise destroy it instantly, you'd need a very peculiar form of matter. It wasn't ordinary mass. It wasn't even antimatter. It was something we might call exotic matter, material with negative energy density. Let's pause there. Negative energy might sound like science fiction, or a kind of dark magic. But in quantum theory, it has a sliver of reality. There are conditions like those created in the Casimir effect, where energy behaves strangely, where empty space is not truly empty, and fluctuations in the quantum vacuum create effects that, to some observers, mimic negative energy. This negative energy isn't something you can scoop up or store in a battery. It's fleeting, delicate, a side effect of quantum uncertainty. But in Thorne's model, if it could be harnessed, if even a small amount could be arranged just so, it might create the repulsive force needed to hold a wormhole open, to counteract the inward collapse with a gentle outward push. Like propping open a collapsing tunnel with a scaffold made not of steel, but of silence. Of course, no one has found a way to gather or control exotic matter in the quantities required. No one even knows if it can exist in stable forms. But the model worked, in math at least, and that was enough. Enough to publish, enough to inspire, enough to light up a corner of theoretical physics that had long been dim and dusty. And so, the idea spread. Thorne's paper didn't just stay in academic circles, it rippled outward. It influenced not just Contact, but eventually Interstellar, a film that Thorne advised from its earlier stages. In that story, a wormhole appears near Saturn, opening a door to a distant galaxy. The journey is not smooth, not simple, but it is possible. And for once, the science wasn't an afterthought. It was the foundation. It's tempting to dismiss this work as merely speculative, as fanciful curves in the math, with no connection to reality. But there's something quietly profound in what Thorne attempted. He showed that science and storytelling don't have to live on opposite shores. They can meet in the middle, in a tunnel carved by imagination but held together by reason. He also showed that theoretical physics isn't just about answering what is. Sometimes it's about asking what could be if only the universe bent a little more gently. Now let's return to the image of a wormhole. Two mouths, two ends, hovering in space, linked by a throat. If the throat stays open, if the exotic matter holds, then you can step into one side and emerge from the other, perhaps light years away, perhaps years away. Because here's where it gets stranger. If one mouth of the wormhole is kept still while the other is taken on a high-speed journey, perhaps accelerated to near the speed of light, then brought back and rejoined, something unusual happens. Time passes differently for the two mouths. This isn't speculation. It's a well-tested prediction of relativity called time dilation. The travelling mouth would experience less time than the stationary one. When they are brought back together, they are still connected, but out of sync. The wormhole now links 2 points not just in space, but in time. A person entering the stationary mouth might exit through the travelling one into the past, or vice versa. A time machine, born from geometry. This possibility, this gentle twist in logic, opens the door to paradox, and that's where we're headed next. But for now, let's rest with Thorne's contribution. A man who answered a novelist's call with pages of equations, who didn't promise faster-than-light travel, but offered a blueprint for what it would take, who built not a tunnel through space, but a bridge between wonder and theory. And whether or not wormholes can ever be traversed, his work reminds us of something softer, something easier to carry. That imagination, when guided by reason, can curve even the most rigid laws of nature into something that feels like hope. Time is usually something we think we understand. It ticks forward, it passes, it builds layers in our memories, ages the leaves on trees, carries seasons gently into one another. But in the world of relativity, time is not a universal rhythm. It can stretch, it can slow, it can, under the right circumstances, refuse to stay in sync with itself. And when that flexible time is paired with a wormhole, the result is a passage not just through distance, but through history. To begin, let's imagine a pair of wormhole mouths. Like twins born at the same moment, they share a connection, a tunnel between them. You might picture them as two shimmering doorways, one floating near Earth, the other placed somewhere else in the cosmos. In their original state, they are synchronized. If 1 second passes at one mouth, it passes at the other. They are like mirrors held at a distance, each reflecting the now of the other. But now, suppose we take one of those mouths, gently, carefully, and begin to move it. Not slowly, like a leaf drifting on a pond, but with immense speed. We accelerate it, pushing it to a significant fraction of the speed of light. This is not easy. It takes enormous energy, immense precision, but we do it. As it travels, time begins to behave strangely. This is the effect Einstein described with special relativity. From the perspective of the stationary mouth, time for the travelling mouth slows down. Its clocks tick more slowly. Its moments stretch. And when it finally returns, after perhaps only a few years of its own experience, it finds that far more time has passed at home. This is not a trick of perception. It is measurable, testable, real. We've seen this happen in particle accelerators. We've seen it in satellites. The faster you move, the slower you age, relative to someone who stays behind. Now comes the quiet twist. The wormhole has remained intact throughout the journey. The tunnel between the mouths has stayed connected, even as one end has experienced less time. And now, when you peer into the stationary mouth, you're not just seeing across space, you're seeing into the past. Let's say 10 years passed on Earth, while only 2 passed for the mouth that travelled. The connection remains. That means a person could enter the mouth that stayed on Earth and emerge from the other, only to find themselves 8 years earlier. The wormhole has become a time machine, and not just any kind. This is not a device that spins or whirs or pulses with glowing lights. It doesn't tear holes in the fabric of reality or cause thunderclaps in the void. It's quiet, geometric, a gentle slope in the structure of the universe. It works not by violating physics, but by obeying it too well. Of course, there are limits. You can't travel back before the wormhole was created. The time machine only lets you move between the difference in time experienced by the 2 mouths. It is a bounded loop, not an open door to all of history. But still, it's astonishing. It means that under the right conditions, time might not be as linear, as irreversible as we once thought. That earlier and later might not be absolute, but relative. that paths through time might twist, not like roads, but like rivers, and that you, a single traveller, might step into a tunnel and emerge into a version of the past still unfolding. Now pause for a moment. This might feel overwhelming, but it's worth slowing down and letting the image settle. Time, in relativity, is not a single ticking clock. It's a dimension. And just like space, it can be curved by motion, by mass, by geometry. When we treat it with that gentleness, with that sense of shape rather than sequence, these strange effects begin to feel less like paradoxes and more like possibilities. There are metaphors that help. Think of two identical plants, rooted at either end of a long corridor. One sits in sunlight, the other in shade. After a year, the one in light grows taller, fuller, older. The one in shade, growing more slowly, still resembles its younger self. Move between them, and it's like walking into a memory. And if you imagine that corridor as a wormhole, the path doesn't take you across the garden, it takes you through its seasons. Or imagine two old friends with matching watches. One goes on a long journey at high speed, the other stays home. When they reunite, their watches no longer agree, but the friendship remains. And if a tunnel connected their hands through all those years, one could reach back and grasp the other. Out of order, but not out of touch. These aren't just thought experiments. They are the logical consequences of relativity applied to the geometry of wormholes, and they raise profound questions, not just about physics, but about meaning. Because if time can be bent, if its order can be reshaped, then what becomes of causality? What becomes of memory, of choice, of responsibility? What happens when before and after are no longer firm but fluid? That's the territory we begin to enter now. With wormholes that shift in time, we arrive not just at the doorstep of possibility, but at the threshold of paradox. In the next session, we'll wander further into that landscape, into causal loops, grandfather paradoxes, and the delicate idea that maybe, just maybe, there are rules the universe writes not to prevent time travel, but to make sure its stories always end where they began. But for now, let your thoughts drift on the idea that time is not a single path, but a woven field of paths, and in the heart of space-time, if you're careful enough, you might find a corridor that takes you not to where you want to go, but to when. If you could step through a door and find yourself in the past, what would you do? It's an old question, one that lives at the intersection of curiosity and regret. It has filled books and films, thought experiments and quiet midnight musings. Would you warn someone? Change something? Undo a moment or relive one? Time travel invites that kind of tenderness, because it brushes against the most fragile parts of memory, the parts that wish things had gone differently. But physics, in its quiet way, offers a complication. Because when wormholes twist time into a loop, when the past becomes reachable, not as a story, but as a destination, it's not just sentiment that gets tangled, it's causality itself. Let's begin gently, with the most famous paradox of all, the grandfather paradox. Suppose you step through a time-travelling wormhole and arrive decades in the past, before your grandfather met your grandmother. Suppose, through some unlikely chain of events, you prevent that meeting. You stop their first conversation, or change the course of their lives in such a way that your parent is never born. If that happens, then how did you exist to go back in time in the first place? And if you never existed, how could you have interfered? It's a loop, not the gentle kind, but the kind that collapses on itself. A story that erases its own first page, a line of dominoes in a circle, where knocking one over makes the next fall, and the last one topples the first, but not if the first never stood. At first glance, this kind of paradox feels like a showstopper. Surely the universe wouldn't allow this. Surely time must protect itself from contradiction. And yet some physicists have suggested otherwise. In the 1980s, Russian physicist Igor Novikov proposed a principle, a way of threading the needle between freedom and consistency. He called it the Novikov self-consistency principle, and it goes like this. If an event exists that would cause a paradox, then the probability of that event is exactly zero. In other words, time is not fragile. It is not a glass you can shatter by stepping on a crack. Instead, it is a woven path that bends but does not break. If you travel into the past, you cannot change it in a way that creates inconsistency. You are always part of its story. Even if you tried to stop an event, your actions would become part of the very history you sought to rewrite. It's a soothing idea. In this view, the universe is not just logical, but graceful. It allows time travel, but only the kind that loops cleanly. You might nudge a candle, leave behind a strange photograph, or become the reason your grandfather did meet your grandmother after all. But you will not erase yourself. You cannot. The paradox, then, resolves not by forbidding time travel, but by limiting its outcomes. The future is still open, but the past is a fixed narrative, unyielding to edits. Still, some find this unsatisfying. What about free will? If you go back and are destined to do something, then is it truly your choice? If all your actions must align with a consistent timeline, are you really travelling in time or just acting out a scene already written? And this leads us deeper into the strange territory of causal loops, events that seem to cause themselves. Consider a story like this. A scientist, exploring an old library, finds a notebook full of elegant equations. She studies it for years, builds her career around it, and eventually travels back in time to leave that same notebook in the library where she found it. Who then wrote the equations? They exist, but not because someone invented them. They loop. Or imagine a traveller who goes back in time and gives a young musician the melody to a song. The musician writes it, performs it, and inspires the traveller, who will one day go back and give the melody to the young musician. The origin disappears. The effect causes the cause. These are called bootstrap paradoxes. And while they sound absurd, general relativity doesn't necessarily forbid them. If the events involved are self-consistent, if they don't break causality outright, then they may be allowed even if they boggle the mind. But perhaps the most unsettling thing about causal loops isn't the logic. It's the implication that some things might exist without origin. That knowledge, objects, even people, could emerge from loops rather than lines. That the universe might contain echoes with no source. Still, there are ways to soften these ideas. You might think of time not as a straight line, or even a single loop, but as a branching braid. Each strand twists, curves, and sometimes knots with others. Some events are consistent within one strand. Others might leap across into different ones. And this brings us gently to an alternative view, the many worlds interpretation. If our universe splits with every quantum choice, then perhaps each paradox simply resolves itself in a new branch. If you travel back and change something, you do not alter your own timeline, but create, or arrive, into another. There, your grandfather never meets your grandmother, but you came from a different branch. The contradiction dissolves. Your past remains untouched. You didn't erase yourself. You changed the context. In this view, the universe is endlessly generous. It doesn't prevent contradiction, it roots around it. Every decision, every action spins out another world. The loop still closes, but not in a circle, in a spiral, always turning, never quite returning. Of course, none of these ideas have been tested. Causal loops, paradoxes, branching universes, they are shadows cast by equations and imagined machines. But even shadows can teach us something. About the flexibility of time, about the fragility of logic, about the strange poetry that emerges when you try to fold a straight line into a loop and still expect it to make sense. In the next session, we'll meet Stephen Hawking's answer to all this. The idea that maybe, just maybe, the universe forbids time travel altogether, not through contradiction, but through instability. that perhaps every time a wormhole might allow a trip into the past, something intervenes. Space vibrates, energy spikes, the tunnel collapses. Not because time travel is impossible, but because the universe defends itself. But for now, sit with the idea that time may loop, that your future could visit your past, that some stories might begin and end in the same place, not as a flaw in the narrative, but as its quiet design. Stephen Hawking once held a party for time travellers. He sent no invitations until after the date had passed. Balloons were hung, champagne was chilled, and chairs were arranged in a semicircle, waiting. No one came, and Hawking, with that blend of playfulness and profound insight that so often marked his work, took it as subtle evidence for a theory he had long suspected, that time travel to the past is not merely improbable, but impossible. Not because we can't imagine it, not because the equations forbid it, but because the universe itself doesn't allow it to function. He called this idea the chronology protection conjecture, a gentle name for a fierce defence. According to this hypothesis, any attempt to build a time machine, a traversable wormhole that links the future to the past, would be sabotaged not by paradoxes but by physics itself. That nature would intervene, that quantum effects, usually so delicate, would roar into action, destabilising the wormhole the moment it threatened to allow time travel. To understand why, we have to zoom in, down to the quantum level, where uncertainty dances in every empty space. Wormholes, as we've discussed, are tunnels through space-time, and if they're manipulated to link different points in time, they become potential time machines. But this creates a problem. Light, particles, and even virtual particles, the ghostly fluctuations of empty space, can loop through the wormhole repeatedly. They can re-enter the past end of the wormhole and circle back over and over, amplifying with each loop. Like a microphone placed too close to a speaker, the system feeds back into itself. A whisper becomes a howl. This is called a quantum instability. The energy density at the wormhole's throat begins to climb, fast. Radiation piles up, stress energy tensors spike, and before long, the wormhole tears apart. Or, more precisely, it collapses into something else, likely a black hole. The universe doesn't slam the door on time travel. It simply nudges the hinge until the door falls off. This is the heart of Hawking's proposal. He wasn't saying time machines violate the laws of physics. He was saying that the laws of physics might prevent them from ever being used. That every attempt to build a causal loop would be undone by the very structure of space and time, responding to the threat of contradiction. In a way, it's an elegant solution to a messy problem. The Novikov self-consistency principle allows time loops but forbids paradoxes. The many worlds interpretation allows changes to the past but splits the universe. Hawking's chronology protection cuts more cleanly. Don't go back. Not because you'll destroy time, but because time will destroy the mechanism you used to try. It's a poetic idea that the universe has a kind of immune system, not just for physical intrusions, but for logical ones. That it resists being rewritten. That every tunnel to the past, no matter how carefully built, is quietly erased by the reality it threatens. And yet, Hawking's conjecture is just that, a conjecture. It hasn't been proven. The quantum field calculations involved are notoriously difficult, and while simulations support the basic intuition, no one has yet found a full theory of quantum gravity that can answer definitively. It's a whisper in the math, not a law chiselled in stone. Still, it fits. It resonates with the way the universe often behaves, not by saying no, but by making certain paths too costly, too unstable, too fleeting to follow. And in that way, it reflects something deeper about our place in time. We are beings who remember, not beings who return. We move forward, one moment at a time, carried by entropy, by causality, by the slow unfolding of the universe's timeline. Time travel tempts us because it offers a way out of that flow, a way back, a way to fix, to undo, to reach across the chasm of what has already happened and touch it once more. But maybe that's not how it's meant to be. Maybe memory is the only form of time travel we're supposed to have. Maybe regret and longing and wonder are our mind's versions of wormholes, fleeting connections to other times, made not of exotic matter, but of thought. And perhaps that's enough. Because in the end, even if wormholes can't allow us to return to the past, they still allow us to imagine it, to model it, to explore what it would mean. And in that imagining, there is beauty. Not in the machines we can build, but in the questions we're willing to ask. Hawking's work didn't kill the dream of time travel. It shaped it. It gave it rules and boundaries, like the edges of a garden. It told us that the universe is coherent, not rigid, but self-aware in a strange mechanical way. That causality matters, that stories must make sense, even when they bend. And so, the party for time travellers remains empty, the champagne untouched, the clock silent. But the questions linger. Could we ever build a stable wormhole? Could quantum gravity, once fully understood, open loopholes we've yet to imagine? Or will the universe continue to guard its timeline, letting us look back, but never step? We don't know, and maybe that's the point. In our next session, we'll begin exploring how these ideas have evolved, from the quantum foam of Wheeler's dreams to the latest models that suggest wormholes might exist, but only as shadows or signals or tunnels through the mathematics themselves. Structures not for machines to pass through, but for information. Because even if we can't go, perhaps the universe still lets our thoughts arrive. You might imagine a vacuum as something still, a perfect silence in space, a blank canvas with nothing to say. But quantum physics insists that this silence is never complete. Even in the deepest emptiness, there is a murmur, a flicker, a restless, invisible dance. This is the strange truth of quantum fields. According to our best understanding, every point in space is filled with fluctuating fields. Even when no particles are present, these fields are never zero. They jitter, they buzz, they respond to the uncertainty at the heart of all things. And from this quiet chaos, something remarkable emerges. A force, a pressure, a tug of nothing pulling something together. This is the Casimir effect, a delicate experiment first proposed in 1948 by Dutch physicist Hendrik Casimir. It began not with wormholes or time machines or entangled particles, but with two simple metal plates, placed very close together in a vacuum. The idea was that in the vast openness of space, these plates would block certain wavelengths of vacuum fluctuations. Like walls in a room that silence some echoes while amplifying others, the plates would limit which virtual particles could flicker into existence between them. Outside the plates, the full symphony of vacuum energy would play. But between them, only a restricted set of notes could be heard. And so, from this imbalance, this subtle asymmetry, a pressure builds. The plates are pushed together, not by gravity, not by electromagnetism, but by nothing. Or rather, by the restless somethings that quantum theory tells us always emerge from nothing. This effect is tiny, but measurable. It has been observed and confirmed many times, and its implications reach far beyond its delicate setup. Because the Casimir effect shows us that the vacuum is not a void, it is a field, a canvas humming with possibility. And among the many strange results that emerge from this hum is the idea of negative energy. In certain frames, the energy density between the plates can be considered less than the surrounding vacuum. This is not negative in the way we use the word in everyday life. It doesn't mean harmful or subtractive in a moral sense. It means that, compared to the baseline energy of the vacuum, this region has less. A dip below zero. A kind of quantum shadow. And here is where the connection to wormholes begins. To keep a wormhole open, To prevent it from collapsing under the immense gravity that its geometry implies, you would need something to push outward. Not ordinary pressure, not mass, but negative energy. Something that defies the usual pull of space-time and instead repels. Ordinary matter doesn't do this. It falls, it clumps, it obeys the laws of attraction. But negative energy bends those laws. It pushes outward. It creates the possibility of supporting strange shapes in space-time, like wormholes. The Casimir effect doesn't give us this energy in the amounts or configurations we'd need to stabilize a wormhole, but it proves that negative energy is not a fantasy. It's real, though rare and difficult to control. It's not exotic matter from science fiction. It's a subtle whisper of the quantum world, a confirmation that even the most outlandish ideas in theoretical physics sometimes have small echoes in reality. And it makes us wonder, if two metal plates resting silently in a vacuum can summon a force from nothing, what else might space be hiding? Could fluctuations like these appear elsewhere? Could they, under the right conditions, be gathered, shaped, amplified? Could they one day offer the scaffolding for something larger? A tunnel, a passage, a bridge? We don't know. And yet even asking the question is valuable, because the Casimir effect teaches us to take nothing seriously, to treat emptiness not as the absence of being, but as a field of becoming. It invites us to look again at the blank spaces in our theories and see them not as failures, but as stages, waiting for the next flicker, the next possibility. In a way, it's humbling. The most extreme structures in the universe, black holes, wormholes, the very geometry of space-time, may depend not on massive stars or exotic particles, but on the behaviour of space itself when left alone, on the patterns that emerge from quiet. It also reframes how we think about building or engineering wormholes. Perhaps the real work doesn't lie in smashing particles or harnessing gravity, but in listening, in measuring the quiet, in learning how to shape the restless fluctuations of vacuum itself. In the next session, we'll see what happens when physicists try to do just that, not with metal plates, but with the intricate circuits of quantum computers. In 2022, a group of researchers announced they had simulated a wormhole, not in space, but in math, encoded in entangled qubits. It wasn't travel, it wasn't teleportation, but it might be a step toward understanding. But before we go there, let the image linger. Two plates, a vacuum, nothing in between. And yet, there is movement, there is pressure, there is a force emerging not from action, but from the mere presence of possibility. And that perhaps is what wormholes are too. Not shortcuts, not science fiction doors, but forces born from geometry. Possibility shaped by silence. In late 2022, news headlines around the world carried a curious phrase: physicists create a wormhole in a quantum computer. The words moved quickly, bouncing from scientific journals to popular media, from cautious optimism to speculative excitement. But behind the headlines, behind the bold declarations and artistic renderings of space-bending tunnels, was something quieter, more subtle, and in a way more beautiful. No wormhole was built. No starship vanished into a swirling tunnel. No traveller stepped into one end and emerged light years away. What was built was not a machine, but a model. Not a passage through space, but a passage through understanding. To make sense of what happened, let's take a step back into the world of holography. Not the kind used for security stickers or concert illusions, but the deeper mathematical kind that has reshaped how physicists think about space, information, and the edge of the universe. This begins with the idea of the holographic principle. It suggests that everything inside a volume of space, all the matter, all the energy, all the gravity, might be described entirely by information encoded on its boundary. like a three-dimensional world generated from a two-dimensional script. This is more than metaphor. In certain theoretical frameworks, particularly those involving anti-de Sitter space and conformal field theory, known together as ADS-CFT, this principle becomes mathematically precise. In that framework, a wormhole, called an Einstein-Rosen bridge, can be understood not as a tunnel in space, but as a particular configuration of quantum entanglement on the boundary. From the outside, it's just a set of correlated states. From the inside, it looks like a connected space. Now, back to the quantum lab. A group of researchers, including Maria Spiropoulou and Daniel Jafris, designed an experiment using a small-scale quantum computer, a machine capable of simulating the behaviour of quantum systems. They crafted a specific set of interactions inspired by the ADS-CFT correspondence. The system was small, only a few qubits, but carefully prepared to mirror the mathematical description of a traversable wormhole in a simplified universe. They did not simulate the entire universe, or even an entire wormhole. Instead, they simulated how information might move through a wormhole-like structure. In the model, they inserted a message, an encoded quantum state, on one side of the system, and watched it emerge, intact, on the other. To those who had studied the math, this resembled what might happen if information was sent through a tiny traversable wormhole. Not a wormhole you could fly through, not a tunnel with walls or curvature, but a structure where information moved in a way that mimicked how it might in a true wormhole geometry. This was not a breakthrough in engineering. It was not a confirmation that wormholes exist. It was a step in understanding, one that gently stitched together geometry and quantum circuits, theory and experiment. And it mattered. Because for decades, wormholes lived in the realm of paper. Beautiful solutions to equations, fascinating diagrams, sometimes toyed with in science fiction, but never tested. This experiment didn't change that completely, but it narrowed the distance between the imagined and the explored. It showed that, in principle, certain behaviours associated with wormholes could be modelled, could be made manifest, not in the cosmos, but in the lab. It's like building a miniature wind tunnel to test a design for wings. The wind isn't real, the flight's not taking place, but the behaviour tells you something true, something measurable. It also reframes what it means to build a wormhole. Maybe the future of wormhole research isn't about bending space-time with colossal machines. Maybe it's about subtle manipulations of quantum states, carefully designed symmetries, and correlations that mimic geometry. Maybe wormholes, at their most essential, are not tunnels through matter, but tunnels through correlation. Pathways that information follows, not particles. This idea brings us back to the concept of ER equals EPR, the possibility that every entangled pair of particles is connected, however faintly, by a microscopic wormhole. In that view, the simulation wasn't pretending to create a wormhole, it was expressing one. It was demonstrating that entanglement and geometry might not be different things, but two languages describing the same structure. Of course, limitations remain. The simulated wormhole was deeply simplified. It existed only in a toy model of quantum gravity. The geometry was emergent, not physical. The system used only a few qubits, and scaling it up would introduce immense technical challenges. No space-time was actually curved, no distance was actually crossed. But understanding doesn't always begin with triumph, sometimes it begins with imitation. And that's what this experiment offered. Not proof, but echo. Not a bridge you can walk through, but one you can recognise in the math. In a strange way, it's poetic. We didn't build a wormhole, we whispered one into being, inside a machine made of frozen atoms and lasers. We didn't travel across the stars, but we glimpsed, through the lens of quantum circuits, what such a journey might feel like if you were made not of matter, information. In the next session, we'll go deeper into this link between entanglement and space. We'll we'll explore the ER equals EPR conjecture and what it means to say that space is built from relationships. It's a concept that reshapes everything. Because if true, it means wormholes aren't rare anomalies in the universe. They are its foundation. Imagine two particles far apart, so far that no signal, no wave, no burst of light could ever reach one from the other without taking years, maybe centuries. Yet somehow they remain in sync. Measure one, and the other seems to know. Flip one, and the other answers. It's not communication, it's something deeper, a bond that exists not across space but beneath it. This is entanglement, a phenomenon so strange that Einstein once called it spooky action at distance. He didn't like it. To him, it felt incomplete, an artifact of a theory still unfinished. But over time, quantum mechanics proved itself again and again, and entanglement emerged not as a flaw, but as a feature. A thread invisible to classical eyes, but unmistakable in the math. Now, imagine those same particles, but instead of picturing them as points, picture them as end points of a tunnel. A wormhole. Nothing that matter could pass through. Nothing you could shine a light into. But still, some kind of connection. Not in the space between them, but in the structure of their shared state. That's the bold idea behind a conjecture known as ER equals EPR, proposed in 2013 by two of the most influential minds in theoretical physics, Juan Maldacena and Leonard Susskind. This idea begins by joining two papers from different eras. One, from Einstein and Rosen in 1935, described wormholes, tunnels in space-time, later called Einstein-Rosen bridges. The other, also from 1935, was the famous EPR paper, Einstein, Podolsky and Rosen, introducing entanglement and questioning whether quantum mechanics was complete. Maldacena and Susskind suggested something wild, that these weren't separate ideas, that every entangled pair of particles is connected by a microscopic wormhole, that space-time geometry and quantum entanglement aren't just metaphorically linked, but literally the same thing viewed from different angles. If this is true, then space itself may be woven not from distances and coordinates, but from relationships. This turns everything on its head. Instead of thinking of particles first, and entanglement second, we start with correlation, with connection. Space isn't the backdrop against which physics unfolds, it's the result of physics unfolding. Wormholes aren't rare accidents, they are the architecture that underlies the world. They aren't shortcuts through space, they are space. And here's where it becomes quietly poetic. If space is built from entanglement, then the universe is not a vast emptiness occasionally sprinkled with things. It is a fabric of interwoven stories. Each particle, each event is part of a network, linked by threads you cannot see, but which shape every distance, every interaction, every possibility. It means that the structure of reality is not made of blocks, it's made of bonds. This interpretation is still young, still being debated, still being explored, but it solves a problem that has long haunted physics: how to reconcile the smooth curves of general relativity with the jittering uncertainty of quantum mechanics. General relativity describes space-time as a geometric object, curved by mass, stretched by energy. It's continuous, elegant, deeply classical. Quantum mechanics, on the other hand, deals in probabilities and jumps. It refuses smoothness. It speaks in uncertainty. But if space-time is not fundamental, if it emerges from quantum states, then the conflict dissolves. Geometry becomes a shadow of deeper entanglement patterns. Wormholes become the natural bridges within this deeper structure. This also reframes our understanding of black holes. In the standard picture, a black hole is a one-way street. Information falls in and cannot escape. But in the ER equals EPR framework, if two black holes are entangled, They're connected by a wormhole, not one you can traverse, but one that links their quantum information. When information enters one black hole, it isn't lost. It becomes encoded in the bridge. It still exists, just elsewhere. This solves, or at least softens, the black hole information paradox, a problem that had challenged Hawking and others for decades. It also deepens our understanding of how gravity and quantum theory might be connected. In this view, gravity itself, the curvature of spacetime, is not a primary force, but a statistical average of many tiny entangled threads pulling in all directions. In a way, it's as if the universe whispers to itself. Each entangled particle pair is a syllable, each connection a sentence, each wormhole a breath between phrases, and what we call reality, what we move through, measure and remember, is the quiet song they form together. This interpretation is still speculative. It lacks experimental confirmation. No one has seen a wormhole between entangled particles, but in the math, in the models, in the way the ideas fit together, something resonates, and it offers a new kind of dream. Wormholes don't have to be engineered. They don't need vast energy or exotic matter. They're already here, all around us, stitched into the fabric of entangled particles. We don't need to make them. We need to understand that they are the signature of a deeper truth, that space is not a container, but a consequence. In the next session, we'll explore how this insight leads to another startling idea, that the entire universe might be a hologram, that what we experience as three-dimensional space could be a projection from a distant boundary, and that wormholes, once again, might be the silent links between the map and the territory, the edges and the interior. But for now, let the thoughts settle gently. That space is not made of things, it's made of between. And the wormholes we seek are not rare gaps in space-time, but the threads that hold it together. Try to imagine this. A three-dimensional world full of colour, motion and depth. But every detail, every interaction, every force you feel is encoded on a two-dimensional surface you cannot see. It's like living inside a sphere, unaware that everything you experience, your thoughts, your body, the stars you glimpse overhead, has its mathematical origins not inside the sphere but on its outer skin. This is the essence of the holographic principle, a theory that began as an abstract mathematical insight and has grown into one of the most compelling and strangest ideas in modern physics. And once again, wormholes are quietly involved, threading their way through the edges of space, not as tunnels for travel, but as bridges of meaning. The principle finds its most precise expression in something called AD-S-CFT duality, a theoretical framework proposed in 1997 by Juan Maldacena. At its core, this duality states that a gravitational theory inside a space called anti-de Sitter space, ADS, is exactly equivalent to a conformal field theory, CFT, defined on its boundary. Every particle, every wave, every bend in space-time inside the volume corresponds perfectly to interactions happening along the outer edge. It's a kind of cosmic mirroring. What's inside is fully described by what's outside. This may sound implausible, but mathematically, it holds. And in the strange architecture of AD space, a kind of curved space that's often used in theoretical physics because of its well-behaved boundaries, this mapping is beautifully exact. If you know the rules on the surface, you know the story within. Now, where do wormholes fit into this? Suppose we have two separate AD spaces, each with its own boundary, each with its own conformal field theory. On the surface, they are disconnected. But if the boundary theories are entangled, then the spaces inside may become connected by a wormhole. This idea brings together everything we've been exploring so far: holography, entanglement, geometry. The wormhole doesn't appear as a separate object. It emerges from the correlations between the boundaries. It is not built from mass or matter. It is built from information, from relationships, from the same threads that make up ER equals EPR. You might picture it like two paintings on opposite walls. Each seems separate. But look closely, and you see brushstrokes that mirror each other, movements that echo, a single pattern, split across frames. Now imagine that this connection goes so deep that the space between them becomes a tunnel, not one made of paint or canvas, but of shared meaning. In this view, wormholes are not disruptions in space-time. They are affirmations of it. Not shortcuts, but expressions of coherence. They arise naturally when the universe is entangled with itself. This idea also helps us understand how space and gravity might be emergent. If the gravitational field inside ad space is fully encoded on its boundary, then space-time itself may not be fundamental. It may be an illusion, not in the sense that it isn't real, but in the sense that it arises from something deeper. Much like temperature emerges from the motion of atoms, or a melody emerges from vibrating strings, space-time might emerge from the symphony of entanglement on the edge. The wormhole in this metaphor becomes not a break in the fabric, but a particularly elegant harmony, a bridge that exists only because the song is whole. The holographic principle also reframes the black hole paradox in a fascinating way. According to this model, the information that seems to vanish into a black hole is actually preserved, not in the unreachable interior but on the surface. The black hole becomes a kind of hologram. What happens inside is written on the outside, and the wormhole, once again, may represent the continuity of that information, linking the two realms through entanglement. Of course, our universe is not exactly an adies space. It appears to be expanding, not curled inward. But physicists believe that some version of the holographic principle may still apply, perhaps in ways we don't yet fully understand. The boundary may not be physical, it may be mathematical, conceptual, a limit not of location, but of knowledge. And this is where the metaphor deepens. What if reality, as we experience it, is always a kind of hologram? What if everything we see, depth, distance, motion, is a projection of something richer, thinner, stranger? What if wormholes are not rips in this projection, but clues to its structure? It's a humbling thought, that what we call real may be just one layer of a multi-dimensional narrative, that every moment, every measurement, every flicker of light is the visible trace of an invisible story, written not in matter, but in code. In this view, wormholes do not violate the rules. They are the rules, made visible for a moment. They are not fantasies of faster-than-light travel. They are reminders that space and time are not the end of the story. They are its unfolding. In the next session, the final one before our quiet wind-down, we'll return to the latest models. We'll meet the 2019 proposal for a traversable wormhole that requires no exotic matter, and yet remains too slow to be useful. We'll ask, honestly, whether wormholes will ever be more than metaphors, and we'll rest in the idea that even if they aren't real in the way science fiction dreams, they may be real in another way, a way just as meaningful. But for now, let the idea settle. That space might not be space, that boundaries might hold the whole, that wormholes, when they appear in our theories, are not openings into other places, but reflections of how deeply everything is already connected. In 2019, a team of physicists from Harvard proposed something that, at first glance, sounded like science fiction taking a cautious step into the realm of theory. They had found a way, mathematically at least, to describe a traversable wormhole that required no exotic matter, no negative energy, no violation of the energy conditions that have long stood as gatekeepers at the thresholds of speculative physics. It was small news in a way, not shouted across headlines, but in the quiet halls of theoretical physics it echoed, because up to that point the idea of a stable wormhole, a tunnel through space-time that remained open long enough for something to travel through, seemed to require ingredients the universe stubbornly refused to provide: negative energy, exotic matter, hypothetical constructions that never emerged naturally. But now, here was a model that didn't require cheating. It obeyed the known rules of quantum field theory. It followed the mathematics like a quiet traveller following a trail. And yet, there was a catch. Always a catch. The wormhole in this model was traversable, but not practical. It allowed signals to pass through, but only very slowly. Slower than light would travel if it simply took the scenic route through ordinary space. There was no advantage in speed, no promise of instant travel between stars, no shortcutting the fabric of reality. Instead, this wormhole offered something else. Not convenience, but coherence. It existed not to get us somewhere faster, but to show that such structures can, in principle, emerge from the laws we already trust. That they are not ruled out. That the universe may permit them, not because they're useful, but because they're possible. And perhaps in a way that's more meaningful, because it shifts the role of wormholes from tools to truths, from speculative engines of travel to quiet demonstrations of the universe's capacity for complexity. The model used a concept called quantum teleportation, not in the Star Trek sense, but in the carefully defined way physicists use the term, transferring quantum information from one place to another using entangled particles and classical communication. In this context, the wormhole became a geometric manifestation of that process. The teleportation protocol and the traversable wormhole were two sides of the same structure, one described in quantum language, the other in gravitational language. It was a realization of the deep duality we've been circling throughout this part of our journey, that gravity and entanglement may not be competing descriptions of the universe, but complementary ones. That one can be translated into the other, like poems written in two different languages, each carrying the same meaning with slightly different rhythms. So, does this mean wormholes are real? That depends on what we mean by real. If we mean something you can fly a ship through, then not yet. If we mean something you could build in a lab, even a miniature version, then we are still far from that threshold. But if we mean something that the mathematics of our universe allows, something that emerges naturally from the interplay of gravity and quantum mechanics, then yes, wormholes are not ruled out. They are not violations, they are possibilities. More than that, they are reflections. They reflect how space and time might emerge from relationships. They reflect how information and geometry might not be separate concepts. They reflect, most poetically, how connection, however abstract, can give rise to structure. In this light, wormholes are not just speculative curiosities. They are philosophical instruments, ways for the universe to explore itself, to ask what it means to be connected, what it means to move, what it means to remain whole across distance and time. They are perhaps the universe thinking out loud, like a mathematician scribbling in the margins, testing new forms, knowing they may never be used but needing to ask the question anyway. Or a dreamer drawing doorways in the air, not because she plans to walk through them, but because she wonders if they could be drawn at all. And perhaps that's why wormholes remain so present in our stories. Not because we expect to use them, but because they represent something deeply human, the hope that there's more than one way to cross a distance. That connection is possible even across the unimaginable. They ask us to imagine a universe where points are not just locations, but relationships, where distances can fold, where paths can surprise, where the structure of space is not a fixed stage but a fluid possibility. In the end, whether wormholes are ever built may not matter as much as the fact that we can conceive of them, that our theories make space for them, that the equations, when allowed to wander, sometimes draw loops and bridges and tunnels, places not to go but to imagine going. And in that imagining we discover something else. We discover ourselves. Because physics, at its core, is not just a study of the universe, it's a mirror. Every theory is a question we ask about reality, and every answer reflects a little more of who we are. Curious, precise, poetic, stubborn, capable of inventing impossible doorways, not to escape the universe, but to understand it better. And so, wormholes remain. Not as shortcuts, but as signposts. Not as machines, but as metaphors. They mark the places where our theories touch, where our ideas braid together, where imagination meets structure. In the final part of our journey, we'll gently close this thread, not with answers, but with reflections. We'll let the universe settle around us once more. We'll remember that even when the tunnels remain theoretical, the questions they raise are real, and maybe that's enough. Somewhere along the way, as we traced the lines of equations and wandered through the strange garden of modern physics, the idea of a wormhole stopped being just a shape in space-time. It became something else, something quieter, not an invention, but an invitation, not a destination, but a feeling. Because long before we could write down the math, we were already dreaming of shortcuts, not because we were lazy, but because we were human. We longed to cross distance, to touch someone across an ocean, to return to a moment already past, to find again what had been lost. We wished, quietly, for the world to bend just a little, for the path to be shorter, for the ache of separation to ease. A wormhole in this sense is not just a tunnel through space-time. It is a metaphor for connection in a universe that so often feels vast, slow, and far too quiet. And that's why we care about them, not only because of what they might do, but because of what they represent. A wormhole is the softest kind of rebellion. The idea that the rules of distance might not be as fixed as they seem, that perhaps beneath the surface there's a logic more generous than geometry, that maybe, just maybe, there's a way through. It speaks to the part of us that misses someone who is no longer near. It speaks to the child who wants to see their future, and to the elder who wishes they could whisper advice back through the years. It speaks to the scientist lying awake at night, wondering if two entangled particles really do feel the echo of each other's existence, no matter how far apart they drift. And in all those moments, the wormhole isn't a mechanism, it's a metaphor for hope, for reunion, for the quiet idea that some distances aren't permanent. So when we explore wormholes through the lens of physics, when we map their structure, study their limitations, weigh the impossible materials they might require, we're not just working through equations. We're participating in something older. We're expressing, in the language of science, the yearning that has always lived at the edge of the human story, the desire to belong, to reconnect, to arrive. In myths, it was magical bridges. In dreams, it was flying. In science fiction, it was warp drives and stargates and folds in space. In general relativity, it is the Einstein-Rosen bridge. In quantum gravity, it may be entangled states stitched into geometry. And in poetry, it is simply the hope that two hearts might feel less far apart. Every shortcut we've ever longed for carries the same quiet question. Is there another way? Another way to reach? Another way to understand? Another way to be together, even when time or space seems to keep us apart? Sometimes we want that shortcut to be real, to work, to be something we can build, test, walk through. But more often it is enough to imagine it, to hold the possibility, to let it whisper to us, in the background of the day, that maybe not all roads are as long as they appear. This too is what science does. It doesn't just explain, it listens, it dreams alongside us. And wormholes are one of its most beautiful dreams. They may never open wide in our skies. No spacecraft may ever vanish into one and reappear elsewhere, but they will remain, etched in our theories, folded into our metaphors, drifting quietly through our stories. They will remain, because they are expressions of something real, not in engineering, but in emotion. The realness of longing, the realness of asking what else might be possible, the realness of believing that connection can persist even when separated by silence, by years, by light. And in this way, every time we speak of wormholes, we're not escaping reality. We're honouring it. We're giving voice to the soft parts of experience that science, at its best, never forgets. The way we miss, the way we remember, the way we hope. So let's not be disappointed if wormholes never become doorways. Let's be grateful that they became metaphors. Let's rest in the idea that our best theories, when taken to their limits, don't just describe the universe. Sometimes they describe us. In the final session, we'll close gently, letting go of the questions, the models, the diagrams. We'll drift back into stillness, carrying only the feeling that somewhere, hidden in the structure of the cosmos, the idea of a bridge was always there, waiting not to be built, but to be understood. And in understanding it, we may find that the journey it offers is not across space, but inward, towards stillness, toward connection, towards sleep. There is a kind of stillness that follows curiosity, a quietness that isn't empty but full of everything we've wondered, imagined, and gently set down. And as we reach the final step in our journey tonight, that's where we are, in that soft, reflective space after the questions have stretched as far as they can go, and the answers have begun to fold themselves into silence. Wormholes may not exist in the way science fiction has promised. They may never glow open above us or deliver visitors from distant stars. They may remain buried in the mathematics, too small or too strange to ever hold us. But what they offer, the possibility of connection beyond separation, of coherence across distance, of structure born from longing, is real in another sense. Real not as object, but as meaning. You are made of atoms that once drifted in darkness, scattered across collapsing stars, born from the nuclear hum of ancient suns. There was a time, many times, when those atoms could not touch, could not know each other, could not even exist in the same breath. But now, here they are. Here you are, breathing, listening, thinking. Made of what was once impossible to gather. That's a kind of wormhole too. Not a tunnel in space, but a bridge in time. A reunion written in matter. And tonight, as you rest, you're surrounded by bridges. Between you and the person you used to be. Between now and the moment just ahead, where your thoughts begin to soften. Between your mind and the quiet cosmos that inspired it to wonder. We often think of space as something to cross, a thing that keeps things apart. But space is also what holds things together. It's the room between stars where gravity can stretch, where light can travel, where signals can whisper across decades. It is not the absence of closeness. It is the medium through which closeness is made possible. And perhaps that's the secret wormholes have been carrying all along. Not that distance can be defeated, but that connection can be found even within it. The universe is vast, yes, but it is not careless. It is full of hidden symmetries, subtle links, echoes that answer each other across time. If you look closely, it is always trying to tell a story where nothing is entirely alone, where information remembers, where bonds outlast the paths they once travelled. Even now, as your body lies still, your thoughts are drifting, across ideas, across memories, across images that may fade before you can hold them. That drifting, too, is a kind of travel, and the soft landing that follows is your own kind of arrival. If wormholes are real, they are not in the sky. They are here, in the way a memory can return, uninvited but welcome. In the way a word from someone you love can cross years and still be true. In the way understanding can leap between minds separated by oceans, generations, or silence. The bridge doesn't need to be made of matter. Sometimes all it needs to be made of is meaning. So as you lie here, listening to the last few ripples of thought, know this. The universe that gave you your atoms, your questions, your restlessness, also gave you this moment, this pause, this gentle hush. And in that hush, everything we've explored tonight is still present. The folding of space, the paradoxes of time, the hidden energy of the vacuum, the flickering foam of space-time beneath perception, the bridges we can't build, but can still believe in. They're all here, and if your mind wants to revisit them, later or never, that's okay. You don't need to carry them forward. They've already done what they came to do. They invited you to wonder, and now they invite you to sleep. Not with a command, not with certainty, but with softness, with the calm that comes after a long conversation with the universe, a conversation that didn't demand resolution, only participation. So sleep. Little bridge that might be real. Sleep beneath stars that bend time and remember everything. Sleep beneath a sky that writes tunnels in its equations. Not because they must exist, but because even the fabric of reality wants to know how connection might work. And sleep knowing that no matter how far the answers lie, your questions have already crossed the distance.